Okay, so I'm going to draw on here and I'm going to be doing some problems and we're looking at some right triangle trigonometry. These first parts are kind of interesting because even though it's introduced in this idea of right triangle trigonometry, it's really similarity. So this is right triangle similarity, you could say. It's a little bit different there. Okay, so I have this stuff here, and what's going on with it? How do I see this? All right, here's what's happening. I count three triangles, and maybe I can do this in like three colors here. So here's like one triangle, thing, and then here's another triangle this way, and then there's a third triangle that goes all the way around the outside, and you got three of them, and they're all similar, meaning that they all have corresponding parts. So let's see if I have my big one. There it is. And then I have like a medium one, I guess you could say. And then I got a little one. I got this little baby one. Okay, so with those three items, let's see what I have. On the black one, this x is the hypotenuse because it's across from that 90-degree angle. It's that longer side, so there's my x. The 36 has the shorter leg, so that would go here. And then I have, all right, the big blue one, same color, I guess. The long side of the blue one is 100, and the short side of that is x. And then I don't really have a whole lot of information about the red one, but I guess I suppose because this is 36 and this is 100, I could subtract those and get this one. That'd be 64. So there's that information in there, and that means the long leg is 64. And I don't know what this one is here, the hypotenuse of the red. I don't know what this short leg of the red is either. But that's okay because now I have enough information where pieces are corresponding. I got these two corresponding and these two corresponding. So let's say I did like, the triangles, and that would be, x over 36 here. I'm using the two triangles. Then the two boxes, I could say 100 over x, set them equal to and solve. So let's say I solve that and multiply across each way. You'd have x squared equals 3600. No big deal there. Pretty cool stuff. Then you just square root it. But I noticed that this is really 36 times 100, which is 6 times 6 times 10 times 10, which is really 60 times 60, which is really 60 squared. And x squared equals 60 squared, therefore x equals 60. That was like a piece of cake, and that's kind of how we go about doing that. So first kind of draw these triangles, draw them, and then go back and try to find the pieces that match. And you're going to have pieces that match, but you just got to kind of match them appropriately. So let's erase this and now look at number 3. So I'm going to look at number 3. Let's zoom in here. So we're going to zoom in on number 3. That's a little far. Can we step out? I guess that's about as good as it's going to get there. All right, so here's number 3. Now, again, I have the 3 triangles. Now I got like a small one and a medium one and a large one, and they're all similar, meaning that corresponding parts make proportional scale. So we can set an equal fraction. Now for the small one, I see that I have the 12 and the 9 here as the legs on the small one. So I'm going to put 9 and 12. Now I could find this side over here if I really wanted to. I don't have to, but I could. But that's a Pythagorean theorem, and I could just do 9 squared plus 12 squared equals, and what would that be? 81, 144. You put that together, you should get 225, which is equal to 15 squared. So that'd be just 15 right there. That's interesting. And then the 12 is also the long leg for the medium one. And the x, or short leg for the medium one, I guess. And the x is the long leg. There we go. So I got 9, 12. I can't really take that back. I'm going to put like a triangle around this 12, and I'll put a triangle around this x and circle around this 12. So what that's telling me is I got pieces that match. I got this x and 12, And then I got this 12 and 9. Cool. Now I could simplify this, because 12 is really 4 times 3, and this is really 3 times 3, and 3's make a 1 there, so that x over 12 equals 4/3. Then you multiply both sides by 12, and you get x equals 48 over 3, or you could simplify again, and you got 16. So x equals 16. So kind of interesting there. Just redraw your shapes and see, what's left over. Cool. I can zoom out and it'll become really tiny writing. Look how much writing I fit in that little tiny space. I'm going to erase that. All right, let's move on to maybe something slightly more challenging. For it to kind of zoom in on something else here. All right, now this is like piece of cake. It's almost too easy that it's ridiculous. But just the idea of using Pythagorean theorem. So I'm going to draw on this page here as well. Let's see what we got. So we got 3 sides, and they add up in such a way that you have, like the leg squared plus the leg squared equals the hypotenuse squared. It doesn't really matter which leg is which leg, but that's how we set them up. So in this case, I would have x squared plus 8 squared equals 11 squared. 8 squared is 64, and 11 squared is 121. Then we got our x squared, and then we could do some simple, arithmetic here. If we subtract 64 from that, that would give us, what, 57? So I'm going to subtract 64, and that would give us 57. And x squared equals 57. X equals square root 57. That's it. That's all we're really doing. It's really practicing that idea of Pythagorean theorem. Now, for each of these, you might have a radical in it. In fact, a lot of them you will. You shouldn't assume that it's just going to work out easily. I want to look at 15 over here because I think there's some simplifying that we can do in that one. So let's take a peek at it. I'll try to kind of separate the work. I'm going to zoom in right down here. Excellent, but too low. We got to get up to that one. All right, so now if I wanted to do this calculation, here's a leg, here's a hypotenuse. How do I know that? Because the hypotenuse is across from the right angle. So I would say x squared plus 12 squared equals 16 squared. Well, 12 squared, that's 144. 16 squared, I think that's 256. And this is x squared. Does that seem right? Yeah, it does seem right. So let's go ahead and do some of the math here. Again, we are going to do some subtraction. You don't always add the two numbers to get the x or the c or whatever that number is. And then subtract 144. Let's see what we come up with. X squared equals, well, that would be a 2. That would be a 1 and a 1. So 112. And let's see. I'm not 100% sure, but I'm pretty sure we can maybe break out some pieces in here. I know that 4 goes into 112 because it goes in, let's see, 25 plus 3 more, 28 times. So I'd have 4 and 28. So 112 is really square root of 4 and square root of 28, and that would be 2 root 28. But I could simplify that even more. And why am I even doing this? Because for some reason, on these multiple choice tests out there, they like to do that. They like to simplify. Well, let's see if we can take 2 root 28, break down the 28 some more. That would be a 4 and a 7. And why am I choosing 4? Well, I'm always looking for those perfect squares because those are easy to square root. All right, so the square root of 4 is just 2. So that's 2 times 2 now times square root of 7. And there's our x. And that would be 4 square root of 7. X equals, there we go, 4 square root of 7. Piece of cake, right? Now, if you would have left it here, that's fine. I just wanted to show you that this one was interesting because you could simplify it if you had to, because you had some type of multiple choice test. All right, so that's the basics with the Pythagorean theorem and the similar right triangles. Following up on this, we're going to be looking a little closer at SOHCAHTOA.